Hello, WAVE students. It's time for lecture 6.3 on fuel types and uses. So you will be in page 5 of your packet right here. We'll be taking notes. You'll be pausing the lecture a couple times and doing some calculations on your own and some predictions of what will happen. So let's get started. All right. So our first, so let's just start with our objectives then, is to identify the types of fuels and their uses, describe the pathway of energy and how to calculate efficiency of fuel use, and define electricity and cogeneration. All right, so the first one we have is wood. So what you'll write in your notes right here is firewood and charcoal, and they're often used in developing countries due to their ease of accessibility and access. Charcoal is not coal. You'll be seeing this a couple times. So we use charcoal and coal for heating and cooking food. Peat, P-E-A-T, peat is partially decomposed material that can be burned for fuel. Okay, partially decomposed organic material that can be burned for fuel. And when you do burn this, so this is peat. You can see this all around here, lots of this. So this is also it's not exactly the same as humus, but it's similar to humus. There's not as much organic material in there. It's more woody, but this is a precursor for coal, but it is not coal. This is coal. So what I'd like you to do on your picture here, you have the same picture in the packet there. So there's 3 types of coal. Peat is not coal, okay, so you should write that in. But with time, heat, and pressure, peat gets transformed into lignite, which is also called brown coal. It has a low heat content, a low sulfur content, and is limited in most areas. This stuff is not good. It's really bad to burn for the environment. Bituminous coal is soft coal, so you should say bituminous. Bituminous is soft coal. It's extensively used as a fuel because of the high heat content, but it usually has a high sulfur content, and when you burn coal, you make sulfur dioxide, which contributes to acid rain. So this is bountiful. It's actually found a lot in China right now. It's the kind of coal that they're using in China the most, which is leading to a lot of air pollution and possibilities of acid rain. But the next form of coal is anthracite coal. So anthracite, you should say that. So bituminous and anthracite are 2 main types of coal, and anthracite is the highest quality of coal. They sometimes call it blue coal because it's so condensed, it almost has this blue look to it. It's the most desirable fuel because it has the lowest amount of sulfur, but the supplies are limited, so it's the most expensive, and we're going to use it up the first. And this is a non-renewable resource, so as soon as it's gone, it's gone. So they're formed under different conditions involving time, heat, and pressure. So how deep it is will have to do with how much pressure is in there. And so it's just a geological thing. If you dig down, you might find anthracite, you might find bituminous, you might find lignite. So it depends on where it is. 3 types of coal: lignite, bituminous, and anthracite. Comes up on the AP exam all the time. The next one is natural gas, and this is mostly methane, CH4. So write down that chemical equation. Natural gas is mostly methane. And then we have tar sands, which are clay, sand, water, and bitumen. Bitumen all together. Bitumen is crude oil, and this is nasty stuff to extract. So we're going to talk about the whole life cycle of all of these things. Okay, so before I show you the answer, don't look at that. On the next page, page 8, you should pause the video and then try to put the pathway of energy in order. So you have a bunch of blank spots and then a little poof for each one. So what's going to happen is you're going to lose energy at each transfer. So you're going to start, I'll give you a hint. The first one is energy resource. So the first thing you put in there is energy resource. So you can mark that off as one of the bullet points. And then you're going to say from the energy resource, what happens next? Then what happens next? What happens next? Okay, all the way. And I'll give you the last one. The last one, number 8, is the end user. So go ahead and pause for just a minute. Okay, and now I'm going to show you the answers. So this is in order. It goes energy resource to extraction, to transportation, to processing, to the combustion of energy, combustion or energy conversion. So when you burn it, that's when you're releasing the energy. Most of the time it's combustion. Then the disposal and transportation of the waste, the electricity generation, the electricity transmission, and then the end user. And at each point along the way, energy is lost. So that's what you're writing in this thing right there. Energy is lost. So if you can cut down on any of these losses, you will increase the total amount of energy that is ended up at the end user. So energy is lost at each step, and there's pollution at each step too. Okay, so the next thing we're going to learn about is energy return on energy investment. Okay, so energy obtained from the fuel divided by the energy invested to obtain the fuel. Like you got to dig the coal out of the ground. That takes a lot of energy to get the coal out of the ground. And the whole reason you're doing it is to use energy. So we need to do this math to figure out if it's going to be worth it in the long run. So you're writing energy obtained from the fuel divided by energy invested to obtain the fuel in that box. And now let's say if you obtain 100 joules of coal and it costs 5 joules to extract the coal, what do you think the energy return is? And then what's a number that is more efficient than a number that is larger or smaller is more efficient and desirable? Okay, so those are the things that you're trying to predict right now. And I'll tell you that anything under a number of 3 cannot be considered a viable energy source. Okay, so we're going to do the calculation for ethanol in just a moment. So what do you think? If you obtain 100 and it costs 5, that's going to be a 20 energy return on energy investment, right? Because 100 divided by 5 is 20. So a larger number is more efficient and desirable. Okay, so let's try with some more real-ish numbers. Okay, so at this point, you can pause and think about which of these is an input and which of these is an output. So there's 2 inputs and there's 2 outputs, and then you're going to calculate the return on energy. All right, so you have to do a little bit of math to figure this out. And then you're going to answer this question. According to these numbers, can ethanol viably replace gasoline as a fuel for cars worldwide based on that number that you just learned about there? So that anything below 3.0 is not a viable energy source. Pause the video, give this a try. And I'll show you the answer. Okay. The growing of the corn is an input, so that takes energy. But converting the corn and distributing it, so making the corn into a fuel, is an input. Burning the ethanol is an output. And pure CO2 byproduct, which is sold to beverage industries as dry ice, is an output. So the last 2 things give you energy, and the first 2 take energy. So to calculate it, you would add together the 2 outputs, right? Because this is the energy obtained from the fuel. So the energy obtained from the fuel is the 2 outputs added together. And that divided by the two inputs added together will give you your ratio. And that ratio is 1.28. So is that good? No, it's not good because the 1.28 is lower than the 3.0. 3.0 is what's required for you to even make it worth your time. However, so the answer is no, it would not be a viable replacement for gasoline. However, look, if you could decrease this distribution number, because the growing doesn't really take that much energy, if you could decrease this distribution number, then it would be worthwhile. So locally, only in localized fashion would it actually work. So there are some places where they actually use ethanol. Okay, the right energy source at the right job. So consider overall system efficiency. So one of the things we can talk about is a conventional water heater versus a tankless water heater. These are things that you might have in your home. So you compare electric water heaters and natural gas water heaters. So natural gas water heaters are tankless, and electric water heaters. Okay, so heating water is a 99% efficiency, and tankless is an 80% efficiency. So if you read through these two and compare them, you'll see. So then sometimes you can find out that the overall efficiency of the tank system could be only 35%. And so if you consider where the electricity is coming from, this would be, so why might the overall efficiency end up being 35%? The answer to that is that the electricity could come from a coal-fired power plant, so it's much less efficient. Okay. So that is the fill in on the packet. Feel free to pause if you need to. Okay, so now let's look at transportation of energy. So I'm going to click through these on the slide, and this is breaking you out over here. Let me just see if I can move this. Sorry. All right. Sorry. So I think I'll still be able to show you all this. So this is megajoules per passenger. What do you think each of these is going to be? So you're going to put in, you're going to try to do this, but wait, I might show you the answers. So you're going to put in airplane, bus, cycling, and heavy truck and car with just two people in it, and see if you can figure out what goes where on this graph. So check it out, pause, and then I'm going to show you. So a bus is the 0.92. All right. Cars are the 2.0. So let me write bus. And then for cars, the 2.1. And then for an aircraft, that's the 2.42. And then lorries, which is like that truck. This is from a British thing. So this is a lorry. Kind of a truck. So you might wonder why the plane is so good, and that's because you're going to carry so many more people. You might have like 300 people on the plane. Okay. All right. So how many megajoules per person are expended to travel the 600 kilometers from San Francisco to LA by air, in a one passenger car or by bus? Or if you carpooled with four people, what would be would that be enough of the most energy efficient way to travel? Okay, so pause and see if you can figure this out. Okay, and then I'm going to show you the answers. So go ahead and pause. Okay, so from using the chart from before, right, from using these numbers, let me just make sure that was clear. Okay, so using these numbers, you're going to calculate this. And now I will show you the answers. So for air, you would have the 2.42 megajoules per person per kilometer per 6,000. So that would give you 1452. For a car, it'd be 2160. And for a bus, it'd be 552. So, yes, it would be a little bit better than a bus. So if you carpooled with 4 people, would that be enough to be most energy efficient way to travel? And yeah, because if you could divide the car energy divided by 4, then 540 megajoules per person. So carpooling ends up being the best way to go if you're going from San Francisco to Los Angeles, which is how my family usually travels. All right, so now we're going to talk about the average estimated fuel economy by model in year. And this is really interesting because it has a lot to do with politics and who's in charge of the government and how that affects our energy efficiency. So I'm going to go through this kind of quick and you can pause to write it down. So in the 1970s, the CAFE was passed, the corporate average fuel economy. In 1975, there was an oil crisis, so laws were passed to make cars more fuel efficient. And you can see it had a huge, dramatic increase in the amount of fuel efficiency. Then in the 80s, we elected a president who deregulated. So they lowered the energy emission standards to help. The Reagan administration deregulated and lowered the standards to help the energy industry, and that happened in 1986. And then the increased preference for light trucks and SUVs kept that going, and you can see that here. There was no increase in energy efficiency all through the 80s, 90s, and 2000s. And then the Obama administration passed new legislation to increase the fuel efficiency. And then people became more interested in hybrids and other fuel efficient vehicles, and now we're moving towards an electric future, most likely. We'll talk about the pros and cons of an electric future. So you want to write this in on that graph and then fill in the information. We can go over this a little bit more in class too, about the history of fuel efficiency. So then this just shows you that as the fuel efficiency went up, the CO2 amounts went down. So, and that makes sense, right? So we got much better and more efficient and we had less CO2 emissions. So that was helped out a lot with global warming. So now fuel economy fluctuates. What does it fluctuate in response to? It fluctuates in response to oil prices, political issues and regulations, consumer demand for different types of vehicles, and development of new technologies. All right, so you want to write that down, development of new technologies. So that's what the fuel economy fluctuates in response to. It should also fluctuate in response to environmental issues, but we haven't been as good at communicating that. Now let's talk about electricity. So this has been a little bit of a long lecture. Take a break, get yourself a cup of tea along the way, and then you need to write down these notes. So electricity. Okay, so much important stuff about electricity. We'll be really tying this in a lot. So electricity can be generated from many sources, different categories. So it's a secondary source of energy. It has to be converted from a primary source. You don't just get electricity. It's not like the lightning in the sky that comes down or something. You have to create it. Okay, so it has to come from a primary source. An energy carrier can move and deliver energy in a convenient and usable form. Wood, dammed water, pressurized air. Electricity itself is clean. There's no pollutants to speak of. And let's just make sure. Electricity is not. Okay, so the production of electricity is not. That's what that says. Okay? So the electricity itself is clean, but the production of electricity is not. Okay? So if I say, is electricity clean? You have to say, it depends. Okay. So this is how it works. You have the electrical grid, and the grid is a network of interconnected transmission lines that connect power plants together and link it with us. So you get the electricity generated, could be burning coal, could be using nuclear power, could be using solar panels, and then it comes to the grid, and then the grid comes out to us. So it's the energy grid. So combined cycle plants are more efficient. They can be up to 60% efficient as opposed to 35% efficient. The combustion of natural gas instead of coal, waste heat, oils water, and used to turn a turbine. Okay, so write those things into your notes. All right, so capacity is the maximum electrical output. All right. So the typical power plant gives about 12,000 megawatts a day. That's 500 megawatt hours. Yeah. Okay. So the capacity factor is the fraction of time a power plant operates in a year. So most thermal power plants can have a capacity factor of 0.9 or more, and renewable like wind may only be 0.25. Nuclear and coal-fired take a long time to fuel up to get to capacity, so they're often left running all the time. It ends up being more efficient to leave them on than to turn them on and off. Okay, and then cogeneration. So that's just like to give you a taste for it, and we're going to get way more into detail about how coal-fired plants work and how nuclear power plants work too. So the cogeneration principle is that you combine heat and power. So you use a fuel to generate electricity and produce heat, because as you're generating electricity, you have a lot of heat. So you can cogenerate because we can use heat to warm things up, to have warmer water going into houses, or to use as a baseline. Okay? All right. So don't look at the next one. Now you should take the little quiz. There's a little practice to do. Okay, and pause. And then I'll show you the answers. So make sure you try it first. Pause. And there's the answers. Okay, so you can check your answers. Make sure you know how to do this math. We'll be practicing much more math along the way. Thanks for sticking with me.